All right, that quiz that we had in class last time, I haven't yet started grading that, but I've got a long list of things that I'm going to accomplish during spring break, and that's on it. So when the scores are available, I'll put it into the grade book. The Monday after spring break, our class lecture will be online that day, and I'll email you with the link and also post it on Blackboard. Then the following class meeting, there's both homework 10, which is due, and then the exam that day. And let me just show you, in the case of homework 10, it's posted on Blackboard right now, and I've included the solution to each of, well, not the solution, the final answer. You need to do the solution, but it does have the final answer for each of the problems. So you can see there's 6 questions. The assignment in total is worth 90 points, and it kind of is revisiting some of the same ground that you just initially got a brief taste on in homework 9. Because homework 10 has some more problems related to expansions and contractions. It's got obstructions like what's the maximum height that can be tolerated prior to choking. And then there are 2, or well, I think maybe 3 problems related to weirs. And that's the subject of the recorded video that's set for Monday the 25th. And the video I'm going to post online far before that, so that if you want to get an early start on finalizing this assignment, all you'd need to do is go through the lecture video that covers weirs and spillways. And these are pretty straightforward equations that you're substituting in anyhow. I think you'd probably be able to figure it out from the textbook resources even without the lecture. But the point is that that assignment's available now, and as you have questions during spring break, I'll be happy to answer them. If you want to get in touch with me via Teams or send an email, just let me know how I can help. You've just turned in phase 2 of the design project. That's the 2 PDF maps. And I talked to a couple of people over the last few days, and it seemed like there was agreement on the idea that once you figure out how to use water gems, that actually it's pretty easy to do the optimization. Like changing the pipe sizes and having it recompute is a pretty straightforward process. And so keep that in mind when I do get the revised demand estimation feedback to you. You may need to change your network if you're going to have a big adjustment in flow rates at any of the locations. And so if you change the flow rates, then that's going to necessitate some further optimization of your network. But even with big changes in flow rate, once you've got the layout of the pipes and you've got the reservoir at the right elevation, then changing the pipe sizes is just a few minutes, and then you can usually converge on an optimal solution pretty quickly. So phase 3 of the design project is going to be due on Monday the 1st. And in today's class, we'll go through a demonstration on how to do reservoir sizing. It is, in terms of points, the smallest part of the project. It's kind of going from hardest to easiest in the project. The demand estimation had the most points. I think took you the most time. You had to do a lot of outside research in order to complete that part of the project. And then the pipe optimization, once you figured out the program, probably went relatively quickly. And then this phase 3 of the design project, you could probably solve that in half an hour if you really understand today's demo. And you have to maybe remind yourself or go through the demo again. Maybe it would take you 2 hours at most. But I think that phase 3 of the design project will be a pleasant surprise, and that's intentional, that the project is loaded so that it actually becomes lighter as the semester goes on. And I know you've got a lot of other things going in other classes as well. So those are the announcements. That's kind of where things are at with the course. We're drawing near to the end of the semester. This is class 29, and if I remember correctly, we only get to 42 by the end of the semester. So it's getting good and late in the semester. Does anybody have any questions on the announcements? So today we're going to finish up a couple of examples related to expansions and contractions. And then we'll do that demonstration with Excel, and I'll show how you need to go through the analysis process to size the reservoir. Okay, so let's look at this example, do the calculations together for a channel which is expanding. And we want to know what is going to be the new flow depth downstream if the channel started off at a width of 3 meters, and then it goes through a relatively gradual transition where we've characterized the C value, and this coefficient removes energy between 1 and 2, so that the specific energy downstream is less than the specific energy upstream was. And so the new change in depth partly reflects the fact that the flow per unit width is different. The flow per unit width is lower than it was before because we have the same flow rate Q, big Q, in the narrow section and in the wide section. The volumetric flow rate is the same, but the flow per unit width, lowercase q, at location 2 is smaller because B is bigger. So partly the change in depth is because of that, but then also we have this energy loss effect that we're going to be accounting for in the equation. So if the new width is 5.7 meters, then what would be our new flow depth downstream? So with this specific energy analysis, we're going to end up with an equation which is cubic. We're going to find the 3 roots, and to know which of the 2 positive roots to select, then we're going to have to, in our earlier calculations, have determined what's the flow regime upstream. So is it supercritical, is it subcritical? So let me just outline kind of what I think the steps are here, and then I'll pause from talking and give you a moment to do the calculations. And so find the flow per unit width at 1, find the critical depth, find the flow per unit width at 2, and then into specific energy equation. So substitute in the specific energy equation, formulate cubic equation, solve for roots. All right, so I'll be circulating around if you get hung up on any one of these steps, if you want to check your answers as we go along. But let me give you a few minutes to solve this one, and then we'll come back together and look at the solution. Okay, well, let's look at this. So we know that this channel, it was narrow, now it's expanding. The original depth was 2.75 meters. So it's expanding. We want to know what's the new depth going to be after the expansion. And I've already talked about before how you can't just necessarily expect it's going to be shallower, which is maybe what instinctively you'd guess, because there's 2 separate things that are happening. There's the change in specific energy because of the change in flow per unit width, but then there's also the energy loss. And so we don't necessarily know the magnitude of which and what effect that's going to have. The channel getting wider, if you have subcritical flow, will make the depth greater if there's no energy loss. But depending on the magnitude of the energy loss, it could make the depth reduced. So we have to dig into the specifics to know for sure. So here we've got the flow per unit width initially, which we utilize to calculate the critical depth. Now this critical depth is the critical depth in the narrower section prior to channel expansion, because it's based on a certain flow per unit width. And so this critical depth, which we calculated upstream, that's not going to be the same critical depth downstream when the channel gets wider. There's going to be a different critical depth downstream. But the reason why this is valuable for us to know is we can compare it to the given flow depth and assess the flow regime. So the flow regime upstream at location 1 is subcritical because the given flow depth of 2.75 is greater than the critical. And I tend to find that a faster way to determine the flow regime than calculating the Froude number, but either way is all right. Then downstream flow per unit width is useful to know because the form of the specific energy equation that I think is good for us here is the flow per unit width. Since the downstream depth is unknown, expressing this in terms of the flow per unit width is good. All right, so here's the form of the specific energy equation, accounting for the energy loss on the right-hand side of the equation. Now, I could have just combined these last two terms together. Like I've got the flow per unit width squared in the numerator. In the denominator is 2g times the depth squared. I could have just said, like by collapsing these two together, I could have said 1.45 times q squared divided. You see what I'm saying? If this is 0.45 and this is 1 times this, then I could have just eliminated this second term altogether and just said 1.45 times this term. But, I mean, in the end, it doesn't complicate things too much. If we look at what we've got on the left-hand side of the equation, where it's just all given values, 2.823. On the right-hand side, y2, meaning the downstream depth, plus 0.223 divided by y2 squared. And then we multiply each term by y2 squared to get it out of the denominator. So then that makes this y2 cubed, because we've multiplied this term, and that term by y2 squared. So algebraically, we rearrange this a little bit to get the cubic equation, and then the three roots, one of which is negative, is immediately eliminated. This root is associated with supercritical flow, which if you add subcritical upstream, nothing about an expansion is going to suddenly make the flow become supercritical. It's on the same slope so far as we know. There is no other obstacle or non-uniformity besides the expansion. So if it was subcritical upstream, it's going to be subcritical downstream. And so that's why we choose this 2.794 meter depth. So what was the original depth? The original depth upstream, 2.75. And it's going to 2.79. So that's a pretty subtle shift. Oftentimes the increase in depth would be larger, except for that we're losing a fair amount of specific energy because of that expansion coefficient of 0.45. So any questions about the process of finding the new depth or solving a cubic equation? I mean, there's a lot. In the last several lectures, you've been solving a lot of cubic equations, and so that really needs to be second nature of negligible difficulty when it comes to the exam after spring break. You have to be able to knock out the solution to the cubic equation really without any kind of struggle, because it's an important part of what we've been doing recently. Okay, so pretty closely related are channel contractions, except that there is the possibility that the channel could be so narrow that it chokes the flow. That possibility doesn't exist with an expansion. Like, there's no expansion so wide that suddenly pooling has to occur upstream. That's not a thing. But there is a channel width that's so narrow that suddenly the flow can't be accommodated through that excessively narrow channel. And so there is the possibility that you could have choked flow. And that's what this example is kind of probing at, is the minimum width downstream that could be used to avoid choking. So you'll remember that when we were talking about steps, we had a few examples dealing with the maximum step height that could be tolerated. And if the delta Z was any larger than that critical step height, then choking would occur. So this is similar to that. This is similar because if the channel becomes any narrower than this minimum width, then it's going to cause choking upstream. So in this example, we're going to neglect any kind of a contraction coefficient. We wouldn't necessarily have to, but just for purposes of illustration, it makes it a little bit more straightforward in probing at the minimum width, if that's the main thing we want to look at in this example. So when you're at that point of almost choking the flow, in the same idea that, when it was the delta Z, if you're just at the maximum tolerable delta Z, you've got critical flow conditions over the obstacle. Remember, that's the most efficient flow condition, which exists at the minimum specific energy. So the same thing is true when the channel becomes really, really narrow. What you've done is you've forced critical flow through this narrow throat. So here's the hint. The minimum specific energy at 2 is equal to E1. We're going to set the amount of energy there is at 1 equal to the minimum at 2, and then we're going to assume that we've got the critical depth downstream. So we're forcing critical conditions at that location. All right. So the steps here. First of all, calculate E1 given the initial flow velocity at 1 of 3 feet per second, the initial width and depth. So we can calculate the specific energy at 1. And then we're going to set the two energies equal to each other, assuming that there's no loss happening from the transition in width. And then we're going to solve for what is the new velocity downstream, the new depth, and so on. So let's go through this together. Rather than me pausing and have you do it, let's say, first of all, E1. Okay, so E1 is going to be the depth, Y1 plus V1 squared divided by 2G. So that's the depth of 5 feet upstream plus the velocity 3 feet per second squared divided by 2 times G, 32.2 feet per second squared, because we're in traditional units here. So the specific energy at 1 is 5.140 feet. So that's how much energy we've got to force the water through that narrow channel downstream. Now, something to keep in mind from like a qualitative perspective, the smallest B will lead to the biggest flow per unit width, lowercase q, for some certain q. So think about flow per unit width. If we make B really narrow, that's increasing the flow per unit width. So we want to know what's the narrowest B that can be tolerated. So another way to phrase that is not how narrow can B be, but what's the largest flow per unit width that we could have with the amount of specific energy that's available at 1. So set the specific energy at 1 equal to the specific energy at 2, and then solve for what is the critical depth. So we're saying that the E minimum at 2 is equal to 5.140 feet. We're saying, let's say that the specific energy at 2 is 5.140 feet, and it's flowing at those critical conditions. So minimum energy means critical depth. And what we know from that simplified 2/3 and 3/2 relationship we've talked about before is for a rectangular channel like we have here, when you've got critical conditions, the specific energy is 3/2 of the critical depth, or the other way to say it is Y sub C is 2/3 E minimum. Okay, so the critical depth is going to be 2/3 times 5.140 feet. So we're saying that the water is going to be flowing at critical depth, and the critical depth downstream at 2 is going to be 3.427 feet. Okay, so the critical depth is 3.427 feet downstream. Now, where is the energy in that critical depth? 2/3 of it is in the depth. 1/3 of it is specific energy when conditions are critical. And so that's going to allow us to find out what's the velocity downstream, because we know this is 2/3 of the specific energy. So the remaining specific energy of 5.140 feet, that's the total specific energy downstream, and 3.427 feet is the depth. So the difference between the two is allocated to the velocity head, v squared divided by 2 times g, 32.2. So the only unknown there is the velocity. So that yields a velocity of 10.50 feet. And if we know the velocity is 10.5 feet, and we know the flow rate overall in the upstream location, we had a depth of 5, a width of 10, and a velocity of 3. So what is the overall volumetric flow rate? I wish I had a bigger whiteboard. Let me erase this stuff at the top here to give myself some extra room. So Q is equal to V times A, V1, A1. And the velocity upstream was 3 feet per second. And then the area was 5 feet by 10 feet. So the overall volumetric flow rate is 150 cubic feet per second. And so at location 2, we know the velocity at 2, and we know Q. So A2 is equal to Q divided by V2. 150 cubic feet per second divided by this velocity of 10.5 feet per second. So that gives us the area downstream, 14.28 feet squared. And then the depth we decided is it's flowing at the critical depth, because that's the definition of like the minimum width that can be tolerated, is it's just about to choke, so it's flowing at the critical depth. So if we know the depth, that gives us the velocity. If we get the velocity, that gives us the area. Area is depth and width. We already knew the depth, so then the only thing remaining is the width. So 4.17 feet, that's kind of a long sequence of if-thens. You know, if you know the velocity, then you can know the flow rate and so on. But so any narrower than 4.17 feet, then the flow per unit width is it's too big, and the flow will choke. So that's as narrow as the channel could get. So let's look. How much did it actually contract? It started off at a width of 10, and it contracted down to 4.17. Any further it would have choked, but this is like right on the verge, they would say, of incipient choking. It means it's not choking yet, but it is flowing at the critical conditions, which is the most efficient flow condition for the least amount of specific energy. So any questions about that one before we move on to the example? All right, let me hand you this reservoir example handout. I'm going to put a spreadsheet file onto Blackboard. If you want to follow along with your computer, you can. If you just want to observe, that's all right too. Let me upload that file for you. The one that you ought to download. So let me tell you the basics of what's happening when it comes to sizing a reservoir. Then we'll open up that Excel file and go through the calculations together. In part 3 of the project, we're going to ask the question, how big should the reservoir be? And the purpose of the reservoir is partly to provide pressure to your network. You'll remember from part 2 of your project that how high on the hill you put the reservoir depends, it causes the pressure in the network. So if you need more pressure in the network, you move the reservoir higher and higher on the hill. But what's the downside of putting it really high on the hill? What's the problem of taking it like up to the top of the hill?
Too much pressure when there's no demand.
Too much pressure when there's no demand. Yeah, so it's this optimization of, not going too high on the hill and then blowing your 850 kilopascal maximum when the demand is 0 at night. But you want to have it high enough on the hill so that you can have plenty of pressure to work with in minimizing those pipes. Because if you have it really close to junction A, like if the reservoir isn't very high on the hill, then you're going to have to make all of your pipes really big because you can't afford to lose much more pressure than you started with. So that's part of these reservoirs, is to pressurize the network. But then we're also going to be using them to deal with the variability in demand throughout the day. So during peak hours, there could be more water being consumed than can be produced. In the hypothetical example that we're working with for this project, I've told you that the water is coming from a spring. There's like a mountain spring up on the hill, and that's where the water's coming from. And I've said, let's assume that the water comes from that mountain spring at a constant rate. Most towns don't use a mountain spring for their water supply. They'd use a drinking water treatment plant. But those drinking water treatment plants aren't able to dial up and dial down their production flows with as much variability as you're likely to see in a 24-hour period. I mean, they can definitely, if there's more demand, they can increase their treatment capacity, but it would be tough for a plant to have a huge range in flows. So if you look at this curve, in the course of 24 hours, it would be tough for a treatment plant to turn itself down to 95% of the average day, and then over the course of only like 18 hours, increase their production by 2.7 times or more. So the purpose of a reservoir is to kind of provide shock absorbers on the demand. It's to have a big supply of finished water available for when it's needed. And so it's cushioning the demand. And so if you have the water coming into the reservoir at a constant rate, then you're able to draw from the reservoir at a variable rate. And then it all works out if the reservoir is big enough. So you want to make the reservoir big enough so that there's always enough water in the reservoir to meet the demand, but you don't want to have the reservoir too big, because then that's a waste of money and you've oversized something that is very costly to construct. So here's the key to picking the correct reservoir size. It's knowing what is the average daily flow rate. And now think about in terms of if you've got variable outflow but a constant inflow to this tank. So the water is going out at a variable rate, but it's coming in at a constant rate. So then think about the area under that line and the area above that line of representing average flow rate. So we've got some tank. The water comes in constant, and the water goes out variable. What does the water level do at night when there's very little water that's being used by the people in the city? How does the water surface change at night?
It goes up.
It goes up because it's filling. It fills at night. But then what about this part of the day, when there's more demand, more out than there is in? What's the water level doing during these evening hours? It's falling down, right. So what we want to do is we want to make the reservoir big enough that at the worst, the water level just almost is empty, but then it starts to fill again. So it's like it's fluctuating through the day, but it never gets empty. We don't want to make the reservoir super big because then it would just be like a lot of leftover water that didn't get consumed. But we want to make it just barely big enough. So here's the key to that. We've got, this is my digitization of the curve. Don't use mine in the project. Use yours in the project. But we're going to use mine for today's example. Okay? So just for the example today, we're going to use these. This is what I said was the high scale. So 100, 1 a.m., 94, 2 a.m., 88, 3 a.m., 98. You get the point. And then here's our peak. Our peak was 274 at 8 p.m. Okay. So here's the spreadsheet we're going to start with. Download it, open it in Excel, and I'm going to show you how to size a reservoir. In the handout I've just given you, it says that the, are there any extra copies of that, by the way? Thank you. So it says that we know that the peak hourly flow is 400 liters per second. That's the sort of thing that you know about your town at this point. It's at the bottom of that summary page, the peak hourly demand. So I'm saying the peak demand is 400 liters per second. Turn on editing. So the peak demand, 400 liters per second. Okay? Now, on the handout, it says, there's a hint down here on the handout. It says, reorder the data so that the first hour, then the flow in is greater than flow out appears at the top. I guess we don't know that yet. Let's calculate the flow out. Let me add something here that's percent of peak and then flow out. Okay, so the percent of peak will be this recording divided by, here's our peak value of the recording, which was 274. I'll anchor the reference there. So 36.5% and so on. Just double click in that corner to have it apply to all of the rows. And of course, at 8 p.m. it should say 1. So that's the fraction of the peak. All right. So now the flow rate out will be 400 liters per second. That's the demand multiplied by the percent of peak. So what this is saying is at midnight, the city is demanding 146, essentially, liters per second. By the way, let me put the units here, just so I don't lose track of that. The flow out, liters per second. Okay, now double click to apply it to all of them, and make sure at 8 p.m., is it saying that the peak demand is 400 liters per second? Yes. Okay, so the inflow, in order for this reservoir to have as much going in as it has going out, this is really important, we have to find out what's the average flow out. So we're going to say that the inflow, so by definition, we are assuming that the flow into the reservoir is equal to the average daily flow out. If it's not, then either the reservoir eventually will overflow or it will empty. We're just going to make sure that as much water goes in as goes out. But we want to find out if it's happening at a steady rate, then what would the inflow rate need to be? So I'm going to do equals average and then calculate the average of all of the outflows. $253.71. Now just to make sure that it doesn't get messed up when I move things around later, I'm going to type in that value here. Right now it's a formula, but I'm going to type in 253.71. 53.71. The reason I did that is I'm going to reorder this list, and if you reorder the list, then the formula references when it's averaged like that could throw a wrench in the works. But the hint that I gave you says reorder the data so that the first hour where the flow in is greater than the flow out. So we know the flow out on an hour-by-hour basis. What is the flow in on an hour-by-hour basis? Well, it's constant. It's just going to always be this 253.71. So it's always that. Oh, I should anchor the reference there. So in the evening, look at the figure. In the evening, there's a certain point where the water level has been draining through the evening, and then it just barely starts to fill. Like, what time of day does it begin to fill again? So when is it that, according to this, the first hour where the flow in is greater than the flow out in the evening? So here's the flow out, here's the flow in. So no, flow in is not greater than flow out. Flow in is not greater than flow out. But at 11 o'clock, flow in, which is this column, is greater than flow out. So I'm going to move the 11 o'clock hour to the top. So now it goes 11 p.m., then midnight, 1, 2, 3, and then it stops. The last row is going to be 10 p.m. So I've just reordered the data so that the first hour of the day when the tank begins to fill, like in this daily cycle, we're saying it starts to fill at night, and night just happens to begin at 11 p.m. So 11 p.m. is that critical hour where it was almost empty, but now it has all night to fill up again. So let's find out the volume in terms of cubic meters during an hourly increment. The volume in is the flow in minus the flow out. So that's just going to give us liters per second. So it's the difference between the two is 49.33 liters per second, and it's during a 1 hour period that this occurs. So now let's multiply that by the number of seconds in an hour, 3,600. Okay, so now that's the number of liters that accumulates during a 1 hour period, but we want to know the number of cubic meters. So now I have to divide by 1,000 to convert liters into cubic meters. So I multiplied by 3,600 seconds per hour, divided by 1,000 liters per cubic meter. So during that 1 hour period, there's 177.59 cubic meters of water that accumulates. All right, I'm under the gun. I'm running low on time. It's going to be worth it if you stick with me for 2 more minutes because we're almost done. Double click to apply that formula down through the entire process. That's the volume in. The volume no, that's the volume. Oh, that's the net difference. Yeah, this is the, that's not the volume in, that's the net volume accumulated. So you see how sometimes it's positive, sometimes it's negative. So yeah, it's the difference between the two. It's the net volume accumulated. We got to make sure we got the right labels on there. So then the net accumulation over time is going to be, if we assumed that it was empty, then the first hour is just how much came in. The next hour is what was in it previously plus the new amount that came in. And if I now apply that down through the whole process, it will it's going to fill the tank. It empties a little, it fills a little bit more, and then the way you know it's right is if it converges back down to 0 at the end of the list. So then how big the reservoir should be is the largest of these. So what is the maximum? Let's use this function equals max, and then put this in as the range. So it finds the largest one, and so the reservoir should be 1.25 times this volume. So that's how big we build it. As for a safety factor, we'd make the reservoir 1.25 times larger than the biggest that it needs to be during this 24-hour cycle. So the largest that was needed, 2503. So where was that? It was at 2503, here. So this is the point where it has the most amount of water. If we stored less water than that, then it would run out before 10 p.m. And that's how you size a reservoir. It's 11:53. I'll pay you back those 3 minutes after spring break. I hope you have a good vacation, and if you've got any questions as you work on the project or the homework, then just let me know.